Long before cranes, computer models, or reinforced concrete, people were already choosing impossible places to build. They raised palaces on isolated rock towers, carved routes into vertical cliffs, and placed fortresses where a single narrow path could stop an army. Centuries later, engineers pushed the same instinct even further. They suspended roads above cloud-filled valleys, buried railways beneath the sea, and trapped rivers behind walls so enormous that the stored water can produce measurable effects on the planet. This is not simply a collection of dangerous attractions. It is a history of human ambition told through places where geography seems to say no. Some survived because their builders understood stone, gravity, and defense. Others survived because modern engineers learned how to correct old mistakes. Together, they reveal a question that has followed civilization for thousands of years. When nature creates a boundary, do humans retreat, or do they build directly across it? One of the clearest examples began as a failure. In Pisa, Italy, a bell tower was placed on ground made of soft layers of sand, clay, and silt. Its foundation was only about 3 meters deep, far too shallow for a structure that would eventually rise nearly 57 meters. By the time builders reached the third level, the earth beneath one side had already begun to settle. The tower leaned, construction paused, and generations inherited a problem they had not created. Over the following centuries, the weight continued pressing unevenly into the soil. The top moved more than 5 meters away from a true vertical line. What should have been a disastrous defect slowly became the city's defining image. Yet fame did not make the danger less real. In 1990, officials closed the tower while engineers searched for a way to preserve the landmark without destroying the very tilt that made it recognizable. The rescue required patience rather than spectacle. Engineers added hundreds of tons of lead as a temporary counterweight, strengthened the foundation, and carefully removed small amounts of soil from beneath the higher side. The goal was not to make the tower perfectly straight. Doing that could have damaged the masonry or erased its historical identity. Instead, the work reduced the lean enough to improve stability while preserving the appearance known around the world. Pisa's tower became a rare monument to both medieval miscalculation and modern restraint. It survives because later engineers did not pretend the original builders had been flawless. They studied the failure, respected the old structure, and changed only what was necessary. In that sense, the tower is more than an architectural curiosity. It is a record of civilization learning how to live with error across 8.5 centuries. Other builders used dangerous terrain deliberately. In the 5th century, the summit of Sigiriya in Sri Lanka became the site of a royal complex nearly 180 meters above the surrounding plains. The rock rises almost alone, with steep faces on nearly every side. Reaching the top meant carrying stone, timber, water, tools, and daily supplies up a route that would challenge visitors even today. Yet the summit held palace foundations, defensive works, living spaces, and a carefully designed water system. Stairways wound through boulders and along exposed rock faces. The height offered security and command of the landscape, but it also imposed a permanent logistical burden. Every necessity had to overcome the same vertical obstacle. Sigiriya shows how power and geography could merge. The rock was not merely a place to build. It was part of the architecture, part of the defense, and part of the message projected to everyone below. In central Greece, the monasteries of Meteora turned isolation into a way of life. Massive sandstone pillars rise from the plain, their summits separated from one another by cliffs and empty air. More than 6 centuries ago, religious communities established monasteries on these restricted platforms, some more than 300 meters above the base. Space was limited, so terraces, balconies, paths, and walls approached the edges of the rock. Access depended on carved steps, narrow bridges, and lifting systems. Even today, cable hoists can carry supplies where ordinary vehicles cannot go. The setting offered protection and solitude, but it demanded constant adaptation. Every delivery, repair, and journey began with the same fact: the monastery was not connected to normal ground. Meteora remains extraordinary because the buildings do not dominate the pillars. They appear to cling to them, transforming inaccessible geology into a permanent human settlement. A different kind of mountain defense appeared at Hochosterwitz in Austria. The fortress stands on a limestone rock roughly 160 meters high, overlooking the surrounding plain. The approach does not rise in a simple straight line. It twists through 14 separate defensive gates, each positioned to slow, expose, and exhaust anyone attempting to advance. Passing one barrier only reveals another turn, another wall, and another controlled space. Here, the road itself became a weapon. The builders used elevation, narrow access, and layered defenses to multiply the strength of the fortress without relying on a single wall. According to the transcript, the stronghold was never captured by direct assault. Whether seen by a soldier centuries ago or a visitor today, the experience is psychological as well as physical. The higher the route climbs, the more clearly the landscape explains why location could matter as much as weapons. Predjama Castle in Slovenia used geology in another way. Rather than standing on a summit, it occupies the mouth of a huge cave beneath a cliff more than 120 meters high. Only one side faces outward. The mountain surrounds the remaining sides, turning natural stone into walls that no mason had to build. Behind the rooms, a passage connects with a cave system extending more than 14 kilometers. During a siege, that hidden route could be used to bring supplies into the castle even when the visible entrance was blocked. The design gave defenders an advantage that seemed almost impossible to overcome, but it also tied the entire structure to a confined opening between cliff and cave. Predjama represents a recurring theme in historical construction. The most successful builders did not always conquer the landscape. Often, they looked for a geological feature that could perform part of the work for them. As travel and trade expanded, builders faced a different challenge: crossing space rather than occupying it. Montenegro's Drvasa Terra Bridge spans a canyon nearly 170 meters deep. Completed in 1940, its 5 concrete arches carry the road for about 365 meters. The largest arch stretches 116 meters without support rising from the canyon floor beneath it. At the time, it was the largest concrete arch road bridge in Europe. The bridge converted a dramatic void into a usable route, transferring the weight of vehicles through a carefully shaped system of arches. Pedestrians and traffic still share the narrow deck, while the Tara River appears far below. Its danger is visible, but its achievement is structural. A bridge does not eliminate the canyon. It creates a controlled path across it, repeatedly carrying loads that would otherwise have to descend and climb through difficult terrain. The Millau Viaduct on Montenegro's Belgrade Bar Railway applied the same principle to trains. The structure is nearly 500 meters long, with the railway deck about 200 meters above the valley floor. When completed in 1973, it was the tallest railway viaduct in the world. 5 enormous concrete piers support the line, including one rising more than 130 meters. Each section had to be assembled at exceptional height and joined into a continuous track capable of carrying heavy rail traffic. Today, a train can cross in less than a minute. That brief journey hides years of planning and construction. Before the viaduct existed, the valley was a major obstacle. Afterward, it became one more segment in a railway. Infrastructure changes how people perceive geography. What was once an impassable gap becomes a momentary view from a window. France's Millau Viaduct pushes that illusion even further. It crosses the Tarn River Valley on 7 massive piers, the tallest reaching 343 meters, higher than the Eiffel Tower. Fog often gathers below the roadway, hiding the valley and lower portions of the supports. Drivers may see only pavement, cables, clouds, and sky, as though the bridge were floating with no ground beneath it. The appearance is dreamlike, but the engineering responds to very real forces. Strong winds sweep through the elevated valley, and the cable-stayed system must keep the deck stable while traffic moves across it. Millau is a modern expression of the same desire seen at Sigiriya and Meteora: gain control of difficult terrain by changing the relationship between people and height. The difference is scale. Ancient builders occupied a rock. Modern engineers created a roadway that passes above an entire landscape. In China's Hubei province, the Sidu River Bridge required an unusual first step. The valley was so deep and rugged that moving the initial guide cable across by conventional equipment was impractical. Engineers used a rocket to carry that first line from one side to the other. Once guide was in place, progressively larger cables could be pulled across until the main suspension system took shape. The roadway stands nearly 500 meters above the river, connecting 2 mountainsides without a support pier rising from the valley below. The method sounds theatrical, but it solved a precise construction problem. Before a suspension bridge can span a gap, something must cross the gap first. By turning a rocket into a cable delivery tool, the team transformed an obstacle into a sequence of manageable steps. The bridge opened in 2009 and remains one of the highest suspension bridges described in the source. Cliffside paths reveal the same tension at a human scale. Spain's Caminito del Rey was originally built in the early 20th century so workers could move between hydroelectric facilities. Its famous route follows a gorge wall about 100 meters above the river, with some sections only around 1 meter wide. Steel beams and anchors transfer the walkway's load into the rock. After decades, the old concrete deteriorated, sections cracked or collapsed, and the path was eventually closed. A new walkway was later constructed above the original remains. Visitors now move along a safer route while seeing fragments of the former path still attached to the cliff. The contrast is powerful. It shows how infrastructure can outlive its first purpose, fall in danger, and then be reinterpreted. What began as an industrial access route became a historical experience built around the visible evidence of its own decay. In Spain's Aragon region, the Montfalco walkways solved a route cut off by a reservoir. Instead of carving a conventional road through the mountain, engineers attached more than 500 wooden steps to the limestone cliff. Two major stair sections changed direction repeatedly, climbing above the water on steel beams anchored into the rock. Cable railings mark the outer edge, but the path remains narrow and exposed. The result is not a staircase placed on a mountain. It is a staircase that follows the mountain's vertical surface. The design restored a pedestrian connection by accepting the terrain rather than flattening it. Each turn makes the original problem visible: water below, rock beside the traveler, and no ordinary ground on which to build. The route exists because engineers converted the cliff itself into the supporting structure. Long before such attractions, mountain shelters were built because people needed refuge, not thrills. Cabane de Bertol in the Alps rises in stacked levels from a narrow rocky perch more than 3,300 meters above sea level. The available footprint is so restricted that the building grows upward, with exposed sides opening directly into the surrounding air. Reaching the entrance requires climbing steel ladders anchored into the rock, yet inside is shelter for roughly 80 climbers. In Italy's Dolomites, the Bivacco Buffa di Perero is attached directly to a cliff at about 2,760 meters. Its components were prefabricated below, transported upward, and assembled against the rock. Access depends on a protected climbing route or helicopter. These shelters reveal a practical side of extreme construction. Their isolation is dramatic, but their purpose is simple: create a small zone of survival where weather and terrain offer almost none. Switzerland's Monte Rosa hut expands that idea into a highly self-sufficient building near a glacier at almost 2,900 meters. There are no roads, utility lines, or ordinary water services. Components had to be flown in by helicopter and assembled on site. Its faceted aluminum exterior reflects the mountain light, while the design reduces heat loss and supports solar energy collection. Water capture and wastewater treatment help the hut meet most of its operating needs. The transcript states that it can satisfy about 90% of those needs independently. In an urban building, energy, water, and waste systems are often invisible connections to a larger network. At Monte Rosa, they must function as a compact ecosystem. The hut is not only placed in a remote environment, it is designed to operate with limited dependence on the world beyond that environment. The Tourlitis lighthouse in Greece faces a different form of isolation. It stands on a narrow rock pillar in the Aegean Sea, separated from the mainland and surrounded by waves. The structure occupies almost the entire usable top of the rock. Strong wind and moving water strike the foundation directly, and even maintenance depends on sea conditions. The original lighthouse, dated to the late 19th century, was destroyed during the Second World War, and was rebuilt in 1994 on the same site. A lighthouse normally helps others navigate danger, but this one must first survive danger itself. Its value comes from remaining fixed in a place defined by constant motion. Each storm tests the connection between tower and rock, while each calm interval offers only a temporary opportunity for human access. Water becomes vastly more powerful at the scale of a dam. China's Three Gorges Dam stretches more than 2.3 kilometers across the Yangtze River and rises about 185 meters. Behind it lies a reservoir holding tens of billions of cubic meters of water. That mass applies continuous pressure to the structure and changes the behavior of the river on a regional scale. The transcript notes that NASA has described the stored water as sufficient to slow Earth's rotation by roughly 0.06 microseconds per day and shift the rotational pole by about 2 centimeters. These effects are extremely small, but the comparison communicates the project's scale. The dam is also home to the world's largest hydroelectric station by installed capacity. It is a machine, a barrier, a power source, and a reorganization of geography in a single structure. The Shalongdi Dam on the Yellow River performs an even more visually surprising task. It deliberately releases artificial floods. The Yellow River carries enormous quantities of sediment. If that silt accumulates in the reservoir, storage and flood control capacity decline. Large outlets positioned deep below the waterline allow operators to discharge high-pressure flows downstream. When several gates open together, muddy water erupts from the dam, forming powerful plumes and whirlpools. These operations can move tens to hundreds of millions of tons of sediment back into the river system. Since 2002, the releases have become a regular part of the dam's operation. The spectacle looks destructive, but its purpose is maintenance. The dam stores water and controls flooding partly by creating a controlled flood of its own. It is an example of engineering that works not by stopping a natural process completely, but by managing when and how that process occurs. Bridges over the sea face a slower enemy. The Qinghai Bay Bridge in Dalian stretches more than 6 kilometers across salt water. Wind, spray, humidity, waves, and traffic act on it every day. Salt accelerates corrosion, threatening both exposed steel and the reinforcing material hidden inside concrete. The design therefore depends on protective coatings and concrete engineered to limit seawater penetration. Dozens of piers must carry traffic while remaining surrounded by the environment most capable of degrading them. Construction is only the beginning of such a bridge's life. Its true test is whether materials, inspections, drainage, coatings, and repairs can preserve performance for decades. A sea crossing is not a permanent victory over water. It is a long-term agreement to keep defending the structure against water's chemical and mechanical effects. Japan's Tokyo Bay Aqua-Line solves a sea crossing by dividing the route between bridge and tunnel. The connection between Kawasaki and Kisarazu extends about 15.1 kilometers. Nearly 9.6 kilometers run through an underwater tunnel, while the remaining distance crosses the bay on a bridge. Placing the tunnel beneath the seabed keeps the roadway away from busy shipping traffic above. Ventilation moves air through the enclosed route, pumps manage water, and emergency systems provide protection where drivers cannot simply exit to open land. At the transition stands Yumahataru, an artificial island that functions as a rest area and connection point between tunnel and bridge. The road appears to vanish beneath the sea and later return to daylight. Most of the engineering remains unseen, which is precisely why it works. The complicated systems operate continuously, so the driver experiences an ordinary journey through an extraordinary environment. The Seikan Tunnel reaches deeper into that hidden world. It connects Japan's islands of Honshu and Hokkaido along a route nearly 54 kilometers long, including more than 23 kilometers beneath the seabed of the Sigiriya Strait. Its lowest point is about 240 meters below sea level. Construction began in 1971 and continued for almost 2 decades. Workers excavated through varied rock while groundwater entered the works, forcing drainage and reinforcement systems to expand. Once opened, the tunnel still required ventilation, sensors, emergency stopping areas, and escape provisions. A long undersea railway cannot depend on a single wall keeping the ocean out. Safety comes from layers: geological investigation, lining, pumping, monitoring, maintenance, and plans for emergencies far from either portal. Above, ships cross the strait. Below, trains move through rock in a passage that most travelers experience only as darkness beyond the windows. Across all these places, the pattern is remarkably consistent. Ancient rulers, religious communities, industrial planners, and modern engineers faced landscapes that seemed to deny access: isolated pillars, unstable soil, vertical cliffs, violent rivers, deep valleys, corrosive seas, and rock beneath the ocean. Their solutions were different because their tools and purposes were different. A castle borrowed protection from a cave. A monastery used height for isolation. An arch bridge redirected weight through curves. A suspension bridge carried loads through cables. A dam controlled water by storing it or releasing it. A tunnel survived through drainage, reinforcement, and constant monitoring. None of these structures defeated nature in a final sense. Each one survives by understanding specific forces and staying within specific limits. That may be the most important lesson in this history. The boldest structures are not necessarily those that ignore danger. They are the ones that make danger legible. The Leaning Tower survives because engineers measured movement in soft soil, Alpine bridges close when weather exceeds safe conditions. Undersea tunnels depend on sensors and escape systems. Cliff platforms work because their loads travel back into bedrock. Even ancient sites used narrow approaches, caves, and elevation with a practical understanding of terrain. Human ambition built these places, but observation, maintenance, and respect for limits keep them standing. From a 5th-century palace above Sri Lanka to a railway beneath a Japanese strait, civilization has repeatedly turned impossible geography into architecture. Which of these places best captures that achievement for you? The ancient strongholds, the bridges above the clouds, the dams controlling entire rivers, or the tunnels hidden beneath the sea?